Hi, here we go again. Moving on. So we've got, this time we're going to be looking at how to make particular solutions using the method of undetermined coefficients. I haven't looked at what our differential equation course actually uses, but I'm pretty sure this is how they would be approaching solving constant coefficient ordinary differential equations. So it's a method that allows us to handle many types of inputs fairly quickly. Still a lot of algebra, but it works well. So again, what is a particular solution? Okay, a particular solution uh, for a forced response will be the actual response at steady state. So the forced response, when you go and apply an input into something, all right, so I have a system here and I'm going to come in and I apply an input and it moves, all right. There's two parts to the response for the forced input. There will be, you apply the input and there's a steady state response and then there's a complementary response. And that's the part that attenuates and lead to the point that you just have your steady state solution showing through. Okay, so let's take a look at these. Method of undetermined coefficients. To use this method, first off, you have to have a constant coefficient ordinary differential equation. All right, you can see right here we have one of these things. So in bracket, the n means the nth derivative, n minus first derivative, so on and so forth, down to this coefficient, the first derivative plus a0 times y, so there's no derivative there, equals some factor times our input. All right, so the input for this method to be used has to have the input equal to 0 before time equals 0. So the input starts from 0. And then thereafter, it must be able to be fit into the following form. Okay, you can have an exponential, e to the ht, and then this is a polynomial and a cosine plus another polynomial and a sine. And there's certain conditions on these things. Okay, h and w, so w is the frequency of these sinusoids. That has to be real. And also, this h has to be a real number. So you can't have complex numbers anywhere in this. So it's, e to the 5t, e to the minus 4t. Those are all fine. And then real numbers for our frequencies. All right. Then we have these polynomials that are here. So when you go to check these things out, this polynomial here or that one, they have to be of degree less than or equal to n. See, you have our n right here. But equal to the degree of the input. So what that's saying is I can have an input a t to the m, and that's fine as long as this m is less than or equal to the derivative. So if my input is t to the 10th, but I have just a fifth order differential equation, so 5 derivatives, this method doesn't work. All right? The power on time in the input must be less than the degree in the differential equation, the highest order derivative. So those are the conditions on that. This works for most things, so that's all right. All right? Given that, then based on our input fitting this model, the particular solution can be written as follows. So our e to the ht just comes down, all right? Whichever this m here, so here's our polynomials here. K of t is k0 t to the 0, so this would be k0 by itself plus k1t, blah, 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 all the way up to kmt to the m. Cosine, exact same frequency, all right? Now this is a characteristic of linear equations. If you have a sinusoid at frequency w, you get an output at frequency w. Frequencies flow through, all right? And here we have this other polynomial. It also goes up to the power of m with sine omega t. So as soon as you see this power, then we have to start adding in all these wonderful powers in these polynomials. So these things can start to get a little busy. All right, we're going to see a bunch of examples here, but the first thing we're going to do, everything we do in this course, we do it very incrementally, and so we're going to start solving a first order differential equations. So we're going to apply this to take a look at first order systems for a number of inputs, and we're going to start that in the next video. I'll see you soon. Bye.